Good morning and welcome to the Raman Research Institute. This is kind of very, sentimental meeting for me. I mean, I've been saying this for most meetings that happen at RRI, that, welcome to Raman Research Institute, but I'm really glad to welcome a whole bunch of friends and dear colleagues working at the frontier of cosmology, and to Raman Research Institute, which I would like to speak a bit about. So this is one of the premier institutes of the country, funded by the Department of Science and Technology. But before that, this was founded in 1948 by Raman himself, after he moved from Indian Institute of Science. This ran like his private institute. I mean, the government tried to fund him, but he actually returned the funds because he didn't want to be asked what he was doing. But the institute absolutely did very exciting work, and I want, what came out as a, almost like a discovery for myself, because I knew of Raman Research Institute, but I'm not really too much into history of science. But when I came here, we had the 75th year, and we sort of looked at what are the highlights of great results that came out of the institute. And it, to me, revealed something very unique about the institute. So Raman had a somewhat different point of view of how science should grow in the country post-independence from, the major things that have happened. And this is not to take any sides here. I'm just saying that he felt that, research is kind of something that you have to get immersed in and should be unfettered. So if you go to the library, there's a little archive of his life, and then a quote from him where he sort of described what he imagined this institute will be. And his only thing is, it doesn't say what area or anything. It just says unfettered research at the frontier. So that was his only ask. And that has happened. I mean, we have had fantastic results like Pancharatnam phase, Pancharatnam Berry phase, so which preceded Michael Berry's work by 30 years. And, again, Michael Berry was very, magnanimous to recognize that and kind of highlight that later. And then if you look at the black hole image, Ramesh Narayan at Harvard was a former faculty here. And gravitational waves, there was a group working from the early 90s. This was one of two groups, one at IUCA and one at this thing. So RRI sort of has been able to kind of anticipate areas and, move forward. So at this time, I'm really proud that, there are things we can still talk about. So, my young colleagues here run an experiment called SARES, which I believe is the most sensitive detector in that range where people are looking for the signal of, global signal of reionization. And they had very nice results a few years back, and they're running at various places, and I hope. And then there's an ambitious proposal to ISRO, which is moving along well, to send the similar experiment to the backside of the moon. Not land, but orbit. And we'll see how that goes. And we also, launched X-ray satellite, ExpoSat, in 2000 and, on 1st January 2024. And this was itself something very surprising to me, because the primary payload was, conceived, designed, and built on campus. And what amazed me was the flight model was built here, packed, and sent to ISRO. I haven't seen too many examples of that in my career of, this kind of capability. So I think what sets RRA apart from my experience in other places is something that I have been very keen to see, that science and engineering should work together. Often people accuse me that's because of my initial training. But I cannot imagine doing frontier science without having engineers on board. RRI excelled. This is the only institute where we have scientific staff and engineers at the same level working hand in hand. So SARES, for example, there are 2 faculty members, but the engineers are remarkably, knowledgeable, and they know what they do, right? So similarly in other areas. And this is something, of course, in a small scale in India, I think provides a model, and which is what we have been projecting to the government. And I think there's a lot of understanding that this was something that was missed by many other institutions, of making sure that there's this synergy. So having said that, I'll hand it over to Subir to tell you what the plan of the conference is, and then in the spirit of letting you know what's happening in India, which has been a surprise to me. I mean, I started in 2000 as a faculty, and I was one of, probably the only CMB person and not too many cosmologists, to a fairly capable and large community that we have here. And so Prabha will give a introduction to that. So over to Subir.
Thank you for giving me a whole day's notice to prepare some slides in place of Francois Boucher, who unfortunately had to cancel at the last minute. So as Tarun said, this is a rather special institute. I've had the privilege of being associated with for a few years on the adjunct faculty. And this conference is also rather special in spirit. Oh, thank you. And as the blurb on the webpage says that you would have read, the idea is not to have just another cosmology meeting, but to have the opportunity to discuss and debate about issues that I think are at the back of all our minds, but in the frantic pace of everyday life, writing papers, running projects, etc., we perhaps don't have as much time as you would like to talk to our peers about what we really think is going on and how it should be. And the organizing committee has provided input from a variety of points of view to try and shape this meeting. And I should say that the motivation to hold this actually came from a meeting that we held last year at the Royal Society in London, which was very successful because it was the first such meeting where on a, if you like, a mainstream platform with the participation of, pillars of the cosmological establishment, headed by Lyman's colleague, Jim Peebles, and, Evstathiou Friedman, and many others. We had an opportunity to talk about where were the cracks that we could see in the standard cosmological model today, which is very, very successful, and for the same reason, needs to be scrutinized critically because of its apparent lack of any basis in the fundamental physics that we also pursue today in the other standard model. Now, the talks from all the talks that were given at that meeting are all available on the webpage, but in fact, you can also listen to them on YouTube. Unfortunately, the discussions were not recorded because of concerns about the privacy of the participants. I presume all of you are here voluntarily and willingly and would not mind it being known that you are here to debate the sacrosanct. So unfortunately, the Royal Society did not take that point of view. But what I want to say is that if you look at the program of that meeting, it was in fact broadly similar to the one that we have today, except that the speakers are, of course, rather different. I think the only speaker we have in common between the two is Rick Watkins, who will talk about bulk flow. But apart from that, everyone else is different. And the emphasis is also different because some of the issues that were then relevant, we have moved on from them. So, for example, Wendy told us about the latest developments on the measurement of the Hubble parameter last year. This year, we don't have talks on that. And another aspect that is different is that we have a whole day in this meeting devoted to discussing theory. The previous meeting was focused on simply the empirical evidence. We didn't have much discussion about theory in that meeting. And actually, there were some developments. For example, following Nathan Sechrest's talk on the cosmic dipole anomaly, Chris Clarkson talked about possible theoretical issues why the result might be suspect. But the discussion that followed it, which was in fact led by Jim, made it quite clear that those concerns were unfounded. So in fact, we actually achieved something at that meeting, which was quite significant. And as you can see from these few pictures that I've put together here, including of the final panel discussion at the end, where we asked all the panelists whether the meeting had changed their views in any way. And there were very different answers. I think that is also going to be true here. So John Peacock was adamant that nothing had changed his mind, whereas Jim Peebles, who you see, he said it had actually shaken him, and that it was, I was very pleased when he said that it was the meeting that he had very much enjoyed coming to, and if he ever held it again, we should invite him, which we did. However, maybe India is a little too far for him to travel. And Lyman, it is your job to stick out your legs as far as you can to block the aisle. Okay. Anyway, so as you can see, there was a large, the hall was packed and people participated, and I hope you will do the same. Please don't be shy, speak up and say what you actually think. So since I have to say a little more about the motivation of this meeting, I want to give a little historical background. I mean, many of you know this, but some of you may not. So people say that we have a standard model of cosmology today, and that's actually nothing new in history. Every culture in history has had its cosmology. And the one that ruled in Europe for 2 millennia goes back to Ptolemy and Aristotle, etc., in which, as you know, we are at the center of the universe, and all the planets and the moon and the sun go around us. And in the distance, we see the fixed crystalline sphere on which the stars are embedded. And actually, this does look like what the, this is what the sky looks like. It is a correct description. In fact, this picture is actually taken from Dante Alighieri's road movie, the Divine Comedy, as it were. And he talks about beyond the crystalline sphere, there are converging rays of light ending in an orb of fire. And actually, if you think about it, that's a pretty accurate description of what you would call today the cosmic microwave background. If you interpret this as a projection of a hypersphere, as you'll see in the next slide. But anyway, what happened was after 2,000 years, this picture was overturned, and we had the Copernican revolution. But really, all that happened was that the sun and the earth changed places, as you see here. Everything else remained the same. And this, in fact, had been anticipated already by Aristarchus, 200-something BC, because he had worked out that the sun was at least 20 times further than the moon, and they looked the same size on the sky. Ergo, the sun had to be a lot bigger than the earth or the moon, and therefore he figured it had to be the center of the universe and not the earth. But that was, there was no data, so that is the other thing. We need observations to make things happen. And 400 years later, when Einstein constructed his magnificent theory of general relativity, and we had to construct cosmology, and this was started by the meteorologist Alexander Friedmann in 21, over 100 years ago, this principle was extended further to the cosmological principle. There is some confusion between the two. However, basically, philosophically, they are similarly motivated. We are not the center of anything. But this said the sun is not the center of anything either. And the reason why we need a philosophical principle in cosmology, which we don't really need for other physical sciences, is because it's a very special science. We are restricted in cosmology, as this picture from George Ellis's book shows us, to looking only at what we can see on our past light cone or within it. We cannot, as yet, see things outside our past light cone. In future, we might be able to. There are suggestions using the kinetics and Sunyaev-Zeldovich effect for seeing what other observers Hubble radius away might see in their past light cone, but this is the situation so far. And this is why we need to assume that our position is not special, otherwise we cannot proceed further. And this was codified into the so-called cosmological principle by Milne. And this is the basis for our modern construction. I like this picture, which I took from Joe Silk, because it's actually very similar to the medieval pictures that I showed earlier. We are again at the center of the universe, but this is an arbitrary point. We are sitting on the north pole of some 4-dimensional hypersphere, and the antipodal point is the Big Bang, because light can only come to us along the surface of the sphere, which is why a singular point cannot fill our entire horizon. But as you go back radially, the radial coordinate now is conformal time, or if you like, redshift, as indicated here. You reach a point, if you go further back, as the universe is getting more compact and hotter, where it becomes ionized, and you can't see beyond that point, and this therefore masks the last scattering surface. And you can describe this universe by the Friedman, Lemaitre, Robertson-Walker metric, which I've written down here suggestively to try to look like a Minkowski metric by choosing conformal time as defined here, rather than the regular time. But this is deceptively complicated. Well, it's deceptively simple, but it's actually quite complicated because A, the scale factor, can in fact go to 0. So you can see that thinking in terms of conformal time allows you to represent things simply, but interpreting them is a little more tricky. However, given this simple metric, we can then construct all the tensors that enter Einstein's equations, the Riemann tensor, the curvature, the scalar curvature, etc., and relate them through Newton's constant to the energy momentum tensor of the matter that is filling the universe. And now, because of the simplicity afforded by this maximally symmetric metric, we have, instead of 16 equations, which in any case would be 10 because of symmetry, we reduce it further to just this one equation. And this Friedman-Lemaitre equation results because of the assumed homogeneity and isotropy. This is important to remember. And that is why in this equation we only have 3 terms corresponding to the energy density in matter, the curvature of spatial sections, and this cosmological constant. And if I rewrite it by dividing through by the Hubble parameter square, then I can write it in terms of the cosmic sum rule, which is that the fractional energy densities in matter, curvature, and lambda add up to 1. And this is the standard cosmological model. It's very simple, it's tractable, it is easy to confront with observations, and it is what we are here to discuss, whether that is really the final answer. Now, of course, there is a second equation, and that is relevant for determining the acceleration of that scale factor. And here it is important to notice that although when this was formulated, all we knew about was dust, non-relativistic particles. But in the 1930s, it was realized that what we call particles are excitations of fields, quantum fields that pervade the universe, and those have 0-point fluctuations. And that actually contributes something which looks just like a cosmological constant. We would call it today a super-renormalizable term in the Lagrangian of the standard model. And that adds to this bare parameter, lambda, which is allowed by the symmetry of this equation. There is the underlying general, the local coordinate invariance, and that's what allows me to add a term proportional to the metric. It affects nothing. And therefore, the lambda that we are talking about here is the sum of that little lambda and the contribution from the fields, and these 2 terms know nothing about each other. They are completely independent in a general background, and yet their sum is what enters the Friedman-Lemaitre equation and decides the fate of the universe. And notice that omega lambda is lambda over 3 h0 squared. H0 is the only dimensionful parameter in this problem, and that is what sets the scale of lambda. But because this vacuum energy here has a pressure which is the negative of the energy density, because it has to be Lorentz invariant and look the same to everybody, we have the possibility of acceleration when we look at the Raychaudhuri equations in its simplified form here. And therefore, lambda CDM came to be the standard concordance model because it was discovered, as we all know here, that the Hubble diagram of supernovae seems to suggest that they are accelerating. The expansion is accelerating, having set in relatively recently around redshift of 1. And that gives you this quantity here, 0.8 times omega matter minus 0.6 times omega lambda. The cosmic microwave background, the spots are about a degree in size. So when I expand it in spherical harmonics, the peak will be at 1 degree, because 1 degree, if you saw on the last slide, that was the causal horizon at the last scattering surface. And the position of that peak, which was precisely measured first by WMAP and then by Planck, tells us that the curvature globally, averaged over the universe, is close to 0. Sorry? I'm sorry, yes. Boomerang and maxima before them, yes. Sorry? Name checks. You should have given me 5 rupees earlier, and I would have mentioned it prominently. Anyway, and then we have the measurement of the matter density from, for example, the same oscillations, acoustic oscillations imprinted in the matter. And when you put all this together, as you know, on this simplified picture, which is due to the sum rule again, we have the cosmic microwave background constrained diagonally, the matter constrained vertically, and the supernova constrained diagonally, and we have the so-called concordance. Now, what I want to emphasize is that omega lambda is determined from the sum rule, and lambda then turns out to be of order the present-day Hubble parameter square. The present-day Hubble parameter is neither fundamental nor a constant, yet that is what determines lambda when the data is analyzed in the framework of this model. And I'll leave you to reflect on whether then, when we express that in Planck units and write it as an energy density at a scale of a milli-electron volt, whether that, what that actually can mean in a fundamental sense. Because the actual scale of lambda is being set by the Hubble parameter, which is an infrared scale, which is small because the universe is very large, and that scale is 10 to the minus 42 GeV. It has absolutely no connection with anything that we know about from quantum field theory or string theory or any fundamental theory, where the scale is typically the Planck scale. Yet we interpret this as vacuum energy. Now, there is no connection at all with fundamental physics, and moreover, there is no indication for any change in the law of gravitation at the distance scale that would be associated with the milli-electron volt, which is about a tenth of a millimeter. Now, one more thing I want to emphasize, because Lyman is here, is that notwithstanding the beautiful data from WMAP, Planck, etc., this does not give a direct sensitivity to lambda, to curvature, because here is the table from the Planck paper. I ask you, where is the entry for lambda here? You have baryon density, cold dark matter density, optical depth to loss scattering, etc., etc. But there is no direct sensitivity to lambda. It is inferred from the sum rule. And in principle, we can look for the correlations that would be introduced when lambda begins to dominate between the CMB and large-scale structure because of the late integrated Sachs-Wolf effect. But as SNeIa, who is here, pointed out some years ago, to detect that it's a tiny signal. It's about half a microkelvin. And to detect that at some significance will take 10 million galaxies redshifts over the sky. Well, we are getting there with DESI, but we do not yet have a result in that context. However, we still celebrate ΛCDM in spite of these foundational issues because it gives us a description of how the structure, the cosmic web, as Dick called it, arose from the primordial fluctuations that we saw imprinted on that last scattering surface, just through gravity, with the additional ingredient of dark matter. We need 5.5 times as much dark matter as baryonic matter to have dominated the expansion from before the universe became transparent. Otherwise, you could not have created this structure in time. And this is very, very successful because it allows us to confront this picture with a variety of data, and it is successful in matching all that data. Nevertheless, there are anomalies, and Glenn Starkman will be here shortly, I hope, will discuss these anomalies in the CMB, none of which are major enough to be taken very seriously, but they should be also considered along with other anomalies on large scales. For example, you see a large number of merging clusters. If you calculate how many you would expect to find in ΛCDM, the answer is typically a 10, 1 by 10. Thanks. And there are other anomalies such as great rings and arcs on the sky, and again, they can arise by chance in ΛCDM, but quantifying the probability of that happening is something that is a current issue. And I should say that there is a general feeling that these inconsistencies are often ignored or passed by, in contrast to the situation in particle physics, where as Ashutosh, who is here, will testify, every anomaly is taken seriously, even if it is only 2 or 3 sigma, to see if it actually becomes more significant as increasing the data increases in its extent. And although all those anomalies have eventually go away or are not found to shake the standard model of particle physics, people are not concerned that it will be brought down, because we do think that progress will be only made by going beyond today's standard model. We do not think that it is some religious object that we must worship every day and never entertain the idea of having any fault. And for example, this is something that some of us have been working on, the cosmic dipole anomaly, the mismatch between the microwave background dipole and the dipole in the distribution of large-scale objects, like quasars and radio sources. And this is now found independently from 3 separate catalogs, radio and quasars, to be discrepant at more than 5 sigma in the standard model. And yet, in spite of the fact that most of the obvious systematic issues and the possibility that it's a clustering dipole have been dismissed, this has not yet been taken rather seriously. And rather than talk about it now, Sebastian Hausegger will do it later, I want to simply quote what Jim Peebles said about it. He says, this anomaly is as well established as the Hubble tension, yet the literature on this is much smaller than the hundreds of papers about Hubble tension. And then he says, I expect the difference is an inevitable consequence of the way we behave. I leave you to think about what he might have meant by that. I have no idea. So let me summarize the point of view, which is that the standard model, as I just said, started with the principle that was evoked over 100 years ago, and these foundational assumptions need to be tested. Of course, at that time there was no data, but now we have data. So now we do not have the excuse to say we need to adopt the simplest method possible. We don't need precision. What we need is accuracy. And this distinction is something that my colleague Nathan Seacrest says rather well. He says, remember the Hubble Space Telescope mirror. It was very precisely ground, but to the wrong shape. We want the right shape. We don't want precision. So what I find odd is that even though the data is now here, we are continuing to use these assumptions without testing them. And most recent examples I can think of is, for example, the Dark Energy Survey, and Alexander Refregier, who is here, will talk about lensing in that. There is an unexplained overall shear in the data, and that is simply set by hand to 0 because the universe is meant to be isotropic. And DESI is now promoting evolving dark energy. I have not seen anything in any of the papers, or indeed in discussion with the proponents, as to whether the 30–40% of the sky they cover yields the same BAO signal in every direction. So it is important to pursue these as much as we can with the data that is coming, because I think it would be a real pity if this beautiful data that we are anticipating from Euclid and Rubin-LSST and SPHEREx and other wonderful missions, if that beautiful data were to be analyzed in the straitjacket of this old model dating from 100 years ago without making further progress. And for that, we need new theoretical developments. And let me emphasize that with my last slide, which is an interview I found with Vera Rubin in the oral history project of the American Institute of Physics. And Alan Lightman asked her, she was after all involved in the first measurements of the anomalous local bulk flow, whether her view has been altered from all these observations that she had been part of making. And she says, it has convinced me that we are not living in a homogeneous isotropic universe. This is in 1989. I'm not sure the Robertson-Walker universe exists. But the crucial point, and that is what I want to end by saying, is that this is not unusual. Martin Rees pointed out to me that the evidence for continental drift was around for 30 or more years before it was finally accepted, because nobody had come up with the theory of how continents can move around, plate tectonics. It took that to make the data acceptable. And similarly, she says, if someone came out with a different model that could incorporate large-scale homogeneities, I would be delighted to see it. And I hope that in this meeting, we will make progress towards thinking of a broader spectrum theoretical model that could accommodate this new data that is coming in, and that we do not have to any longer try to massage everything into this constraint of the maximally symmetric space-time that was the most optimal alternative 100 years ago, but which data today is beginning to show has cracks in the edifice. So thank you. I don't suppose we take questions. Prabhakaran. Yes. Oh, sorry, it's here.
Has to be done again. Okay, so I think while they get my slides up, which are just very few, so following up on what Tarun and Subir have said, so Tarun has given me the task of surveying the Indian cosmology scenario, and regardless of what positions and opinions we have regarding the theoretical principles, the main question is, are we in India, within the Indian cosmology community, are we prepared to face the challenges of the future with the deluge of data that is coming? And that is what I would like to present here. Thank you. So since I'm not known to many of you, my name is Prabhabati. And I work at the Indian Institute of Astrophysics, which is about 15 kilometers away from here, down south. So the cosmology landscape in India, I'll start by just giving a summary of the key areas that a lot of people in India are working on. So I had very little time, actually, only yesterday to Google and put this together. So I hope you will forgive me if I miss anything. And also, I know that there are many people here in the audience who were part of shaping the Indian cosmology scene. So if I miss anything, please correct me. So what I found is that we, in India, cosmologists are covering almost all aspects of cosmological questioning today. So the key areas in terms of time scale, time evolution. So there's a lot of work covering the early universe physics, then we had a lot of, we have had and going on ongoing lot of work on the cosmic microwave background. And we also have a very strong group. We have a very strong group working on the cosmic dawn and epoch of reionization physics. So I'll go into the experimental aspects in different slides. So here, these are the key areas. Then we also have a large group working on large-scale structure, structure formation, galaxy evolution, and so on. Then if I organize the subjects into in a different style based on the topics, so we have a large representation for dark matter, people from astroparticle physics. There's interaction between particle physics and astrophysicists, which is very welcome. And we have strong representation in late universe cosmology, dark energy, dark sector, and so on. And many people are here in the audience, and we'll also hear about these in the talks that follow. Then we have strong representation in compact objects, neutron stars, black holes, and whether you can do cosmology with these. We also have gravitational wave cosmology and also gravitational lensing as cosmological probes. Okay, so next I'll move on to the observational endeavors that are going on. So I was quite surprised that there is a very long history and legacy of observational activities in India, which since I was trained as a theorist, I was not really aware of. So it's a learning experience. So I start with the radio observational facilities in India. I think it starts roughly from the year 1970 onwards. This is the time not of inception, but actually first light. There is the Ooty Radio Telescope, which is led by the National Center for Radio Astronomy of TIFR. Then we have the Giant Meter Wave Radio Telescope, GMRT, and the upgraded version, which started operations in around 1996. So I included SARAS, because RRI is one of the, not one, primarily the instrument which has been, the institution which has conceptualized and brought it into actually taking data and being competitive in the world. And Saurabh is leading this now. Then I also found Bengaluru Radio Observatory, where a lot of activity is going on, which is headed by RRI and IAA. Then using the data from GMRT, the radio data, there is a collaboration, the Indian Pulsar Timing Array group in collaboration with Japan, and they have been putting constraints on or detecting stochastic gravitational wave background. And they have been active from 2016 onwards. Then I also found that in telescopes for the infrared, optical, UV, the whole range of electromagnetic spectra, India has a big history, a legacy. And so in my limited research, I found that the Vainu Observatory, which is run by my institute, IIA, this has been operational from 1972 onwards, taking data. Then there is Mount Abu Infrared Observatory, which is headed by the Physical Research Laboratory. Then we have in the Himalayas in Hanle, we have a big observatory called the Indian Astronomical Observatory, which hosts several telescopes in different wavelengths. So there is the Himalayan Chandra telescope, which started taking data from 2001 onwards. And so I organized them based on IR and optical, and these are the high energy X-ray and gamma, MACE, Hagar, and so on. These are run by TFR, BARC, and so on. These ones are also in the same observatory as Hanle telescope, as the Himalayan Chandra telescope. Then we also have recently Dot Devastal Optical Telescope, which was started operating. And for transient study, we have the Growth Telescope, which is run by IIT Bombay astronomers and IIA. Then the ones which are in space, these were payloads which were in space. I think I missed a few of them. So UVIT, the ultraviolet imaging, and X-ray imaging, these two were sent into space they started taking data, and in 2015 they were part of the AstroSat mission. Then very recently we had XPOSAT, which has, I think they had a call for proposals, a second round of call for proposals. Then I want to highlight the international collaborations. So on the left-hand side, I have put the ones which are actually funded and maybe the data is not yet there, but this is already funded and on way. So there is SKA India, TMT India, LIGO India, and then there is a lot of people here are part of the Rubin-LSST collaborations. Then there is the South African Large Telescope, 9.2 meter telescope, of which IUCAA is a part. Then I think RRI was a big part of the MWA in Australia. Then at the individual level, there are several of the active researchers in India who are at the individual level. They are part of various collaborations, JC, Chimes, Hera, Meerkat, Subaru, and so on. Then these are the upcoming and the wish list. So in the upcoming different stages, so I think there is the terahertz telescope, which will come up again in the same location in Hanle in the Himalayas, which is basically led by these institutions. This is already on course. Then in the different feasibility study phases, there is Pratush, I think Tarun had mentioned it, and Daksha. These are going to be in space. And in the proposal stage, there is CMB Bharat, and I think towards the later part of the conference, we'll hear a lot about CMB Bharat. There will be a lot of talks on that, and because Tarun is here, I have put RRI as the lead. And then we have the National Large Optical Telescope, which is called the NLOT, and this was conceptualized more than 25 years ago, but it took a backseat because of TMT being funded, and this is now being revived because of uncertainties related to TMT, and this is going to be in the IR and optical, and right now there is talk that this will be 13.7 meter telescope, and hopefully it will go through. There's a lot of work going on for this, and this is an international collaboration and headed by IIA. Then on the, I have taken extra time, sorry. So there are also the international proposals where various people are contributing. So just to give you an idea of where in India all these activities are happening. So I have marked in red as the centers, research institutions and universities where all these activities are happening. And to my surprise, I found that every single state or union territory has representation, which is great. And I think this were because of the efforts of maybe in historically, we had Rai Chaudhary in West Bengal and Professor Nalikar here, and this has had a cascading effect, and they trained a lot of people and so on. It has mushroomed, and it's very nice to see that this is the case. The blue dots are where the observatories are. This is the Hanle telescope and site where there are actually many. And these are various Uti somewhere here. This is the Vainu Observatory. This is Saras. And you have Mount Abu. And this is the GMRT. And this is LIGO. Yeah. Okay, so this is my last slide, and thank you for your attention. Oh, I didn't know that. Okay. Yeah, I'll add that. Okay. Sorry, we have overshot the time.
Hi, I'm Subinoy, also Prabhat's colleague from IIA. I'll be chairing the session. We are running 10 minutes late, so hopefully we'll cut down the tea time.
I'll be quick.
Our first talk is by Lyman from Princeton on CMB observation. Subtitle is forward.
Here, Joe, that's the microphone on.
So I'll give you 25 minutes.
Sure, it should be pretty
So
close.
35 minutes talk and 5 minutes.
Okay. Great. Can you hear me? It's good. Well, oops, can't see the slides, but that's okay. First, let me give thanks to being invited here. It's great to be back in India. It's yikes, I have to watch out for not falling, and to be here on this beautiful campus. And And I should say, although this will be a little bit, maybe at times a little dowdy, I would love to be one of those taking the data that finds a huge fault in lambda CDM. I mean, it's, the model's there, and the model's there to be challenged, and I think that's really important. But I'm gonna look at some of the challenges to it maybe from a different light. Actually, a little bit along the lines of, I think, the bottom of Sabir's second to last slide. Okay, so I'm gonna, of course, focus on the CMB. And just remind you, right, because the fundamental measurement is a map, and a map can be made by anybody, it has this unique position in cosmology, in that you can make a map in a huge bunch of ways with different technologies, different wavelengths, different strategies, different teams, all that, and you can compare the maps. That's just huge in terms of its robustness. It's more robust than any other measure. You know, I talk with my colleagues working on H0, and I think there are 15 supernova in common for H0 teams in the calibration zone that people have measured. So not that many. Here we have maps. I'll just start the history with COBE. COBE and WMAP are compared. Of course, WMAP and Planck. ACT, Atacama Cosmological Telescope, and Planck. SPT and Planck, right? And we can compare them and mix them and match them and do all those things. We can compare the cosmology from the independent data sets and from cross correlations of the data sets. So this is a really robust situation. And I want to focus a little bit on, in the first part, just telling you, give you an update about where we are with the Atacama Cosmology Telescope. And this is the data release 6. Some of you may have seen these slides. Here's the crew, the leaders who put it together. Our last paper to come out, and I'm going to touch on this briefly, is by Audrey, and he's leading it, and it's about the beam profiles. And you'll see how important those are to get right. And I'll highlight them from among other reasons. Tarun worked on them years ago. Okay, here is the ACT collaboration. It is now, or it's actually ACT is off the mountain. You know, the site is being cleared for, well, I'll show you in a minute, what's called small aperture telescope led by the Japanese team. In its last 10 years, it was led by Suzanne Staggs with Mark Devlin as a deputy, but here's the collaboration. So this is, what I'm going to show you is from data release 6. So here's Planck, about 100 degrees of the sky at 150 gigahertz. And I should say, please interrupt me. Don't give this, you know, especially when I get on. Just interrupt me if I get going too fast here. That's what you add to ACT. And with ACT, or if you added South Pole Telescope, you'd see the same thing. What it does is it overlaps and adds high resolution. And you'll see that, and you can see it here in map space, but you'll see that in a minute in the power spectrum. So this is just the same piece of sky. So I just want to go back, right? This isn't like just one or the other. You could blink for the full ACT data set, the full ACT, you know, the full Planck set here. You'd see more large-scale structure with ACT, but you'd see tons of commons with Planck. You'd see tons of common structure if you just blink the raw data sets back and forth. And you can see what these new experiments are adding, and again, this is from ACT and from the South Pole Telescope. This is the same. This is a bigger swath of sky from Planck. The E modes. That's what you get from ACT, right? The increase in sensitivity in the E modes is enormous, and you'll see how that plays out. And that led to improvements on the cosmological parameters. So what are the caveats observing from the ground? So this is a plot. Let me see if I can, one of these things. Oh, there we go. Good. So if you look at TT, so this is just the noise spectrum versus multipole. If you look at the temperature power spectrum, right, we're dealing with this roiling atmosphere above us, even though we're at above 5,000 meters in Chile. In polarization, the sky's a little cleaner, so it's right down here. But that prevents us from looking at the largest angular scales. And so and I should say, even at the South Pole, this is cleaner, so they can look at slightly larger angular scales. But that's what limits us ultimately. And now, if you go and you look at the raw data, right out of the, you just map it on the sky. These are plots from Sigurd Næss. This is what you'd see, and you'd say, that looks horrible, right? That doesn't look like a nice clean Planck map. And that's just because ground pickup is manifests itself as these horizontal stripes, but you can see they're all large angular scales. So we just filter them, and at very low L, L less than 100. So we don't even look below L of 500 to do our analyses. So you just filter below L of 100, and there's T, and there's Q, and that variation is some large-scale correlated noise, which we also, for Ls, where we don't look. So those are some of the caveats. But you can see, so this is, for this DR6 was largely a blind analysis. A few tweaks were made after it was unblinded, but very, very few. Nothing that would affect these next plots I'm going to show you. So here is the temperature power spectrum, of course, versus L. There's Planck, and without doing anything, that's ACT, right? So this is just a great check, if you will, a complementary data set. And you can see down here, no large scales, much better at small scales.
Just say you're noise dominated below L of 3000.
So that's the atmospheric spectrum. Shouldn't say that's the atmosphere is bigger, but it's common mode. So when we do our maximum likelihood map maker, that's common mode and just disappears. And so we really probe down to here, L of 500. That's where we cut it off. And you can dig into the noise about that much just because of its structure. And we know its structure pretty well. We've spent a lot of time studying it. Here's Planck in EE, the polarization. And there's now polarization from ACT. And it's similar. I have a plot later from the South Pole Telescope, you'll see. There's TE, and there's now with ACT. So big advance, we can do completely separate analyses of these data sets, as I'll get to momentarily. And just from TE alone, we can get a 1.1% estimate of the Hubble parameter. And then, this actually data came out before what I just showed you from DR6. This is Sherwin and Mavroshero led this up. This is a result of a lensing analysis, right? So just to remind you, right, there's the CMB at the photosphere at a redshift of 1100 or so, and that radiation then comes to us, and all the matter between us and the source of last scattering then gravitationally lenses the CMB, and then we can reconstruct it using, basically looking at the 4-point function. So this is a map, and it's not coming through so well here, but this is a map of a huge fraction of the sky, right? And the orange places here from that reconstruction is where the dark matter is, and the darker, the purple points are the voids. Right? We know where the dark matter is. Right? And here it is, a little slice of it, and the South Pole Telescope colleagues see the same thing. Here is another map, but you can see the same data shown slightly differently. Here, these contours are from the Planck CIB measurements, not their cosmology, but their CIB measurements. Because the kernel for the redshift is the kernel for the lensing is about a redshift of 2, and you can overlap them. So you can see where that dark matter is where the cosmic infrared background galaxies clump. Right? It's an amazing check. And you can compute the lensing power spectrum. Here is in Francoeux's paper, and this was a fully blind analysis. So that dark line right there, the thick one, is the Planck anisotropy expectation. And this is, if you'd used the dashed line, was our previous result. And this was a blind analysis with no free parameters, right? And it is a 40 sigma detection of the lensing, or 40 plus now, and it agrees within statistical precision. This is a really powerful test, right? This is now the 3D part of the, getting into the 3D part of the universe. Okay. So here's some parameters, and I wanted to touch on a few things. So P act is Planck plus act, W act is WMAP plus act. And you can just look, and this is this is from our paper. This is what the South Pole Telescope team sees. And you can see, you can scan through any number, any line here, and you can see that they just disagree. That they just agree, and that the chi-squareds to the model are phenomenal. This is chi-squared. It's just, that's it. That's it. You don't need any more parameters here. So this is fantastic. I'd say there's space, ground, adding the DESI BAO. Adding act lensing, it doesn't matter how you do it. You get the same result no matter how you parse this. And I'd say that one thing, and I'll come back to, is for act anyway, and for South Pole Telescope, there's a prior from Planck on tau. But even if you take that away, lambda CDM is still a good model. And then Calabrese and Hill looked at extensions of the model. And I'd say the summary here is we see just taking the DR6 with Planck and with the lensing and with the BAO, no evidence for the sigma 8 tension, no evidence for early dark energy, although in a previous release we saw mild evidence for it, but not with this new release. And this isn't that no isn't that strong. You could squeak it in at a couple sigma. And there's no evidence for more relativistic species in the early universe. The CMB just locks in on H naught of 0.68. And and even combined with DESI, lambda CDM is okay at the 2.5 to 2.8 sigma level. So our bottom line is we don't find any statistical significant departure from lambda CDM. Okay, with that said, is everything great? And this is amazing to me. And I'd say, for me, it's got to be things get interesting at sort of 3 sigma. And again, I would just love to be part of the group that finds the thing that blows lambda CDM away. But there definitely are weeds. It's not all clean. And I just want to focus on 3 of them, neutrinos, beams, and this polarization angle. And when the hope is we find one of these things that's a problem now, a tension, right, that'll grow into something new and beautiful. So let me just say, I'll just point out a few of them. The neutrino mass sum, right? Here are the formal limits, right? It looks like we're, and here's the normal hierarchy. Here's the inverted hierarchy at about 110 milli eV. And so why is this? It's starting to look like we're ruling out neutrinos, yet we have n effective about 3. And so here, that's not true for all data sets, but it's true for a good number, and it was true for at least this recent DESI analysis. But one of the things we find here in pushing is if we remove that prior on tau from Pagano and Jean-Louis, this upper limit increases from 0.057 to 0.81, and this incredible pressure on the neutrino mass sum is released. So there's a lot of room there. So this is not in statistically that rough a shape right now. And if you do this for tau, if you let tau run free or get larger, and it's just by a couple of sigma, it's nothing. Well, lambda CDM is still a good fit, and that DESI discrepancy that I talked about is reduced still further, right? It's ameliorated. And this has been noticed by a bunch of people. So that's interesting and something to keep an eye on, but I think one thing to keep an eye on is tau. Here's a plot I put in because this is a real, this is an experimentalist plot. And this is, as Tarun wrote about many years ago, the effects of your impulse response function of your telescope, the beam, as we call it, are really subtle. And you have to know your beam incredibly well. And it's really hard, and it takes a lot of time. Audrey's been working on it. It's like 1 or 2 people working on it for years. It's really hard because you're looking at parts in 10,000 and parts in 100,000. That's where these effects are. So the recent, here's, and there's no right or wrong here. I'm not going to say that, but just to show you the size of the effect. So the South Pole Telescope team, this is in Guildhall, they had these their original, before unblinding, were those orange data points there. And except when then they looked at lambda CDM from Planck, they saw that it was differ by about 3.5 sigma if averaging over, fitting over 5 parameters, leaving tau out. However, if they assumed that their polarized beam was slightly different, that tension went away. So the message is the beam, these tiny effects are really subtle in how you're dealing with the polarization beam. So this is before our release came out, the ACT release came out. But we agree with their unblinded release, right? So it's, we think the unblinded release is right, and they shouldn't have corrected, and maybe something else is going on. But this is just something to keep an eye on, right? That these, and to keep an eye on these beams. And let me point out something else, which it's out there. It's not talked about that much. Well, amongst, maybe you guys talk about it more. Okay, Minami and Komatsu introduced this method to separate the CMB from other systematic errors and found an intrinsic polarization, an intrinsic angle, right, that's from cosmic birefringence, the rotation of the polarization angle, of about 0.35 degrees at about 3 sigma, something like that. The method doesn't depend on the instrument characterization at all. This is a purely analysis method, which is also something to keep in mind. Here's a compendium. I should just point out before just going to this compendium, this is, as far as I can tell, this is the largest measured discrepancy from lambda CDM if you roll in all the recent data, just period, right? That outside of H0, this is the big one. Okay, and it's related to a physical model, which is neat. Here's this group, Komatsu and colleagues, Diego Palazuelos, updated it. So now it's about 4 sigma, including the recent results from ACT and WMAP. And they caution about systematic errors. Here's the compilation from Sigurd Ness and Thibault Louis and the Diodol paper. And here's 0 right here. But we all want, just systematic errors are not shown, and there are correlations in these data just outright. But everybody measures above 0. This could equally well be negative. So why is that? Everyone's measuring it above 0, but none of us really believe it who are working on the instruments, because this is really, really hard to get right. Here's an example of it being hard to get right. This is in Thibault's paper. This is an array. This is one array of detectors at 90 and 150 gigahertz. And these detectors live at the base of the same feed, right? They share the same feed in the same array. And they can't agree to a few sigma here. And that's just a smoking gun. There's something deep we don't understand here. No matter how much modeling we do, there's something we're missing. Of course, you can average them all together and get a reasonable result and say beta, say the polarization angle is significant. But I mean, if you look at it more carefully, and obviously this is just begging out for higher signals and noise. If you look at it more carefully, you think, yeah, no, there's still systematics error there. And if you look at the Planck data, there are similar things when they tried to measure tau. This is yeah, same result. It's the same data set that went into all those other results I told you about. Okay, so we think it's a systematic that we're still working on, and this is one of the things, this would be incredible if this holds up. But the other thing is this signal is huge, right? That 0.3 degrees. So this is 0.3 degrees. This would mean that we've been making these compendium plots. We're missing what should be on there this whole time, right? That's the EB you get for a beta of 0.3 degrees. It's huge, right? It's just that we haven't plotted. It's just that no one does. It's because we think it's a systematic. Anyway, so we're all watching it. We're all working on making better and better calibrators, and we'll see what the future holds. Okay, brief status. Measuring here. Here's the status. This is pretty up to date. It's got, of course, Planck, ACT, SPT. There it is. I wanted to highlight a measurement that's coming out. So I mentioned the optical depth a couple of times. The class measurement, which is down in Chile, this is this neat paper, Lee, Eimer et al. Through cross-correlation with Planck, they're I think the first ground-based measurement to really start to make inroads to measuring tau. And they agree with the Planck measurement. This is, again, really hard to do because you're going to those large angular scales where there's lots of atmosphere, but you're doing this in polarization, so you use modulation techniques and things like that. But this is a really spectacular measurements. There are a couple of balloon missions that are coming along, the Taurus experiment with a group at Princeton, UC, Toronto, and then DeBernardis and Massey are pulling one together. That's to measure these large angular scales, right? Because that's the signature of tau right down there. And then I'm a proponent. I'm a fan of Lightbird. It's a great experiment. I mean, of course there's all the B-mode stuff. But for tau, it's also fantastic, right? This is the squirreliest of parameters. This is the one that you really have to nail down to further the lambda CDM. Okay, let me touch briefly on the future path here. This is this is a Simons Observatory collaboration. It's large and growing and fun and funded. And Mark Devlin and Suzanne Staggs and Joe Dunkley are the principals right now. Here's what is funded and exists are these, what we call small aperture telescopes, and the large aperture telescope down there. The ones with green diamonds, the large aperture telescope, which I'm not going to talk about at all, but SAT-1 and SAT-3 they're taking data. We have a year in the can for both of those experiments. And they're just looking at large angular scales. The UK group, foundations are poured for all these, and the Japanese group is using the old ACT site to put their telescope in. So all these are being built. So there's hardware, they will arrive. They will get to the site. Why they all look the same? Because it's just a common design. It was easy to share. And they'll all follow this. Here too, this is there are two SATs here. This is the one from our gang, just as we were putting it together down in Chile. And this is the one from a gang centered at UCSD as it's put together looking on the sky. So they'll all look just something like this. To give you an idea, it's great. There are people who work on instrumentation here. This is the picture. So this is, there's 10 centimeters, so roughly 80 centimeters up there. So there's a lens. There's what makes this all work. How you get to low noise at large angular scales is you have to modulate the input signal. So we use a spinning half-wave plate. It's a half-wave plate levitated on magnetic bearings. Spinning at 2 hertz. And ours has been spinning now for a good part of a year. Okay? And then there are cryogenic optics. Everything down there is at 1 Kelvin. These are big chunks of silicon. Those are at 1 Kelvin. Here's a dilution refrigerator. cools our detectors. Our focal plane's at about 60 millikelvin, and there are about 10,000 detectors in there, 10,000 operating detectors in there. It depends on the day, because you can get saturated if there's a lot of water vapor. But there it is, and so again, this is down. These are taking data. I'll show you some preliminary results. So here's just maps of Jupiter, right? We all love to see planets. And then we can look using models of the focal plane, maps of Jupiter, maps of the Moon, maps of Saturn. This is what it looks like. This is what the array looks like. And here's what's different, and actually what makes some of the analysis challenging, is the field of view, the focal plane. It is 35 degrees on the sky. This is enormous, right? And those are each roughly half-degree beams, a little less than half-degree beams, out of each one of those little dots there is half. So this thing just scans the sky. That's all it does. It just scans the sky all day, all night, half-wave plate spinning, and there it is. And it's running right now. And so these are then these two different frequencies. And the Japanese group will add lower frequencies down to 30 and 40 gigahertz. And then the SAT-2, which is in the field and almost observes at 220 and 280 gigahertz so we can get a handle on the dust. Yeah, like a broken bias line, or one of them, multiplexer chips that's not working, something like that. So they're gone. I mean, we can take apart the thing and fix them, but it's just not worth it. Yeah. So they're nominally 12,000. When I say 10,000, that's what we get working on the sky. So here's from first, some of our first indications that it's going all right? To do these things, these big projects, you need to make projections. You have goals and you have baseline. And so these are these detectors, and they were built by NIST in Boulder, and then put actually into functional modules with multiplexers by Suzanne Stagg's group. And you can see we're pretty happy here. Here's our baseline. That was our goal. So we're at least at 90 gigahertz doing better than our goal. And we're doing about at our goal at 150 gigahertz. And this is just for one instrument. And these are good, right? Just to get you, if you have that's 300 microkelvin CMB root seconds. So in 1 second, you can measure 300 microkelvin with a signal to noise of 1 with one detector, okay? And we've got about 5,000 at each for one sat. And we've got 2 sats and the third coming online. So this is really exciting. Here's some preliminary maps. These are from Susanna Azzoni. Here is Simon Observatory Q map, and here is the Planck Q map, to reobserve, to follow the same pattern. So it's looking good. We're recovering lots of, the large-scale structure that we can expect. We can look at the foregrounds. We get a handle on their gain. We're feeling, we're still working on it. We're not publication ready yet. Good efficiencies, looking at beam profiles and all that sort of thing. So all that's going on. Here are maps over a larger scale, and what's amazing to me is we've been measuring T, the temperature at these large angular scales. But you can just look at these QU maps and you can see the signature, right? Vertical and horizontal, and diagonal for U. And that's what the sky looks like. So that's, as I say, this is happening right now. And let me end, I think this is the last slide, with this is a preliminary result, and we're blanking that out because we're still figuring out things at the largest angular scale. But this is just EE, and there's the Planck model. So this has been around for months. This is like with I think, a month of data or something like that, just to start to show that this is coming together. So we're super excited about this. And so where will we get? So this is just the status. The team that's ahead, Right now, and has been so for a while, is the bicep Keck team, and that involves the combining with Planck. Really great limit here. The goal for what I just showed you in 5 years is sigma R of about 0.002, but that's with no extra sats, and that's pretty conservative. And as you know, right, R of an order 0.001 is the prediction of lots of favorite models right now. So we'll see what happens. I think in the long run, as with so many of these things, echoing earlier themes, right, the challenge here is absolutely foregrounds. We see them, of course, and systematic errors. These are tiny, tiny measurements, right? This is measuring, tens of nanokelvin on the sky, like in this, right, tens of nanokelvin just looking up. So it's going to take a while to get right. So let me stop there. Thank you.
Yeah. You have a mic?
It's on. So thanks for bringing up the neutrinos in the first talk. That's really interesting. So it seems to me that what's really happening is that none of the experiments are yet sensitive to the actual neutrino-specific damping of the power spectrum.
Yeah.
What we are picking up is the change in the background cosmology.
Right.
And that's why it's sort of degenerate with W0, WA and things, tau, for example. Mm-hmm. Do you have a sense with Simon's observatory when we will actually start seeing the actual shape of the damping through the CMB lensing, let's say?
Oh, man, I will tell you, I don't have it off the top of my head.
Yeah.
Actually, Dick might remember better. It'll get there.
Yeah,
it'll be a while.
Yeah. Okay.
In years. 5 years.
Okay.
That's the table I remember. But plus, right, there's a lot to be done with, of course, overlapping the surveys and, using the lensing and all that sort of thing. So that will evolve. And as the Large Aperture Telescope, which I didn't talk about at all, which is also at its goal sensitivity, we'll get to, for each, it'll be roughly probably a factor of 3 to 4 deeper than ACT DR6 to give you a sense of scale, right? And you can just scale sigmas by that. So it will be really powerful in cross-correlation and overlaps with lots of surveys. So I think ultimately, that's where things have to go, and that's where you see the tensions as well. So.
Yes, in cross-correlation, one can do a lot tomorrow. I'll be showing some results. And there you can probe this with the large-scale structure.
Yeah, well, yeah.
About Lightbird, which you are a fan of. So the high-frequency instrument of, sorry. Sorry, I can speak.
Yeah.
The HFI on Planck, as you know, was damaged seriously by cosmic rays.
Yeah.
At L2. How is Lightbird going to avoid that?
Okay, so there are some new detector geometries that have been measured and shown to be a lot better at rejecting cosmic rays. So there's awareness of it, and I can't give the specifics, but I saw some results in some review.
Radiation-hardened electronics.
There's that. I think there's just the geometry of how you do the detector as well. And so there are lots of advances. I think the big thing is it's a known problem, and it's
now known, yes.
yeah, and it was it's been known for a while. It's a known problem, and it's being thought about and worked on in geometries, and a lot of people are working on geometries. I think what's this? We all want I don't know how many years it will take. Right? This is still fantastic. We all want another satellite, and so this is just, and it will be bolometric, and so this has just got to be part of it. But there are also, kids might be less sensitive. I don't know the status of those, though. RE, cosmic rays.
Thanks, Lyman, for the nice talk. I'm going to go back to cosmic birefringence that you mentioned.
Yeah.
The difficulties that are there that you mentioned, that it's not easy to make statements about this. Is this related to the fact that we are only asking questions about a global rotation or suppose there was a model which had scale dependence in the rotation.
Right. You have
Would
the
that
power
help?
spectrum of it.
Right. Yeah. So would it help to look for that?
We do. I think we, for ACT, for DR6, Namakawa et al., Dick, do you remember? I looked at it, you remember? Yeah. Saw nothing. The BICEP team has done some really interesting work on this, and it looks, all about this level, and haven't seen anything as a function of angular scale. They have not, though, put out a single number. So they've been focused more on the angular scale. And I think they haven't just because they're still chasing down systematics, and they don't want to say something silly.
So I was just at an inflation meeting in Paris, and everybody wants to take infinitely seriously the very small shifts in NS.
Yes.
And you had the list of all of the NS numbers, which all look so incredibly consistent.
I know.
And yet, Andre Linde and others, it will be the death of these small. And I think there is a lot of overreaction, in spite of the fact that I've been in the game a long time, and it's why we're doing it. But it was just incredible how many people are just sort of mouth agog saying, oh, this is shifted by this small amount. So the one that shifted the most is P-ACT-LB.
Yes, right. It's, yeah.
But you
right
see
there.
that SPT is in good agreement.
Yeah.
With the original Planck results. And ACT, with your tau prior, looks pretty good.
Yeah, there it is.
And so it seems to me that there is much ado about nothing here. It's, one should monitor it because it's going to get better and better, but it's just incredible that theorists are, pardon the expression, so naive.
Well, that's, I'll quote you. No, I think for me, look, this is, let me just say another, I think it's neat that shift can raise such interest.
Yeah, okay, that's
and
another way of
propel
saying
the
it.
field, because we are going to be measuring this much better.
No, absolutely.
And this is absolutely comes down to beam. I mean, beams are among one of the things, just to remind you, right? This is still coming from, largely from the temperature spectrum, and temperature anisotropy, but it's starting to come from both the temperature and the polarization. But just to remind you, for ACT, our 1 over E point of the beam is around 10,000, so right there. But the variations that you see for those, the variations in the beam down here for little changes in NS are tiny. You wouldn't see that error bar on this.
Can I just bring up one other
Yeah.
quick thing here? So the other thing that a lot of theorists got extremely excited about, which I always thought they didn't really look at it right, was the A lens, where
Right.
you do this free parameter. But the thing is, the templates, which is like the differential, they actually didn't look like the data, but because people threw the A lens in, they weren't really looking at does it agree spectrally, which it didn't. And the A lens has gone away with the ACT data, and I think it's true it's gone away with the SPT. So that's sort of a story that's been put to rest.
Yeah, here it is. So here's the Planck A lens. So this is now, and I was trying to get through this, so I didn't pause on this slide. So this is what we call the 2-point lensing. That is, you just add a parameter to the model, and you add a parameter for what lensing would do because it smears the peaks in the CMB. So it's straight from the power spectrum. It has nothing to do with the higher order statistics. And you can see Planck had, it was a little high for Planck. Okay, for us, for ACT in blue, it spot on. The power spectrum just fit lambda CDM, and then combined with WMAP, it's the same, spot on. And actually, when I would talk with Jean-Loup, he would call that the stone in their garden. That's why I changed to weeds. Weeds grow into beautiful things. So that was a stone in their garden, and we have a few more weeds we're taking care of. But that's, I think, what Dick was talking about. So that, I think, has gone away. And now the 2-point agrees with, right, wherever it was, I probably passed it, right there. The 2-point agrees with the 4-point beautifully, which is incredible, right? Just different physics, different, it's just amazing. Different redshifts, different everything.
As we are running late, we can ask questions in the tea break. So let's thank Lyman.
Thank you. Good to.